Hello. In the previous video, we discussed about the difference between calculus and pre-calculus. And we understand that in pre-calculus, we cannot do limit, right? We cannot do anything with limit process. But in calculus, yes, in order to solve the tangent line problem and the area problem, we need to do some limit process. And today we will discuss some examples of limits. Let's consider the following example. I have function f of x equal to x cubed minus 1 over x minus 1. Okay, so when you see a function, of course, the first question about it is the domain of this function, right? The domain of this function. And what is the domain of some function? That is the set of x where the function is well defined, right? Well defined. So I look at this function. The function is well defined when x is not 1, right? Or we say, yeah, when x minus 1 is not 0, right? Or which is equivalent to x is not 1. So that means the domain of this function is the whole number line except one point. Okay, so I can write this is R except 1.1. This symbol is, exclude. Okay, exclude. So exclude 1 point, x equal to 1. That's it. All right, so we have the domain of this function. We know when x equal to 1, the function is not defined. So what happened at x equal to 1? No, that is a very natural question, right? What happened at x equal to 1? The function is not defined, but that is not, the end of the world, right? We still need to understand what happened at 1. That is the beauty of mathematics. Sometimes, when x equal to 2, it's pretty easy. You just plug x equal to 2 into the function, right? And you see the function value right away, f of 2, right? So there's nothing new. There's nothing difficult about, about this when x equal to 2. But when x equal to 1, yes, we still need to consider something in here. All right? So let's do that. I may consider the following way, right? So I have x cubed minus 1. I know when I plug x equal to 1 into this, I get 0. That means, 1 is a 0 of x cubed minus 1. At the same time, 1 is also a 0, right, of the denominator. So I have a hope that when I factor the top and bottom, I may simplify something. Okay? So I plug 1 into the function. I got 0 over 0. That means 1 is the common 0. That is important, okay? The common 0 of the top and the bottom. So let's factor. I have f of x equal to x minus 1. Okay, in here I keep x minus 1 because we all have that. So I have, I can do long division, but we will skip that. I have x squared right here because I know x cubed, right? X cubed in here. I have x to 1 already. Here should be x squared, okay? And then I multiply x squared back, right, with the 1. I say, yeah, we have negative x squared, but we don't have any x squared right here. We don't have. So that means I have to cancel negative x squared. The next term should be plus x. Why? Because x with the x will be x squared. X squared with negative x squared right here will be cancelled out. Make sense? And then I finish with the x. I move to the free coefficient. Here I have negative 1. Here I have negative 1. That means here I should have just plus 1. and that is what I have. Okay, let me erase this. So we already factor this. Okay, and now you see, can we simplify this or not? Because we have x minus 1 and x minus 1. So the question is it equal to x squared plus x plus 1? Of course not. Why? Because on the left hand side, we have seen that the domain of the function f(x) is everything except 1, right? But the domain of this function is the whole number line. We have two different functions over there. Given that when x is not 1, they are equal. But they are different at one point when x equal to 1, okay? They are the same. Let's say that they're the same at any point x, which is different to 1. But they are different at x equal to 1. You see that? Because this function is defined, right? It's defined at 1. You plug 1 into this function, you got 3. But this function is not defined at 1. Because there's no way to divide by 1, right? Or 1 is not in the domain of this function, of the function f. But what is the relation between these two functions? Yes, they are the same at any point x, which is different to 1. That's it. All right? So, there's something strange in here. Makes sense? But that's okay. Let's draw these two functions out and we'll see, right, what is the difference between them. Right now, I don't say anything about, the limit. I just want to talk about the graph of these two functions. Okay? So if we draw it out, one function is parabola, x squared plus x plus 1. So, I will not do that in detail, but, I just want to make this. And I have some point 1 in here. That is 1. Okay. So at 1, I have something right here. Okay. This is the graph of the parabola x squared plus x plus 1. Y equal to x squared plus 1. Okay. And this function is defined on the whole number line. We know that the function f, right, is the same with this function at any point x, which is different to 1. So this is x equal to 1, right? I have to exclude this, from the consideration, right? If we consider the function f of x. So I might have the following picture. Yeah, I have the same curve, right? They are the same. I just draw in different color, right? And there is a hole in here. There is a hole in here for the function f of x. But for other functions, we don't have a hole. You see that? You see? So there is a hole right here. Hole right here. Right? On the graph of the function f of x equal to x cubed minus 1 over x minus 1. And that happened when x equal to 1. Okay? So what can we see on this picture? I can see one thing in this picture. If I pick some point, from here, and I let this point approach to this guy, right? I know how to find the function value in here. It's easy. I just plug x equal to 1 into x squared plus x plus 1, right? You know why? Because if I pick any point in here, right, x is not 1. So we can calculate the function value of fx using the formula of this function. Because they are the same, right? At any point, x, which is different to 1. So this is x. different to 1. Okay, so I can find, you know, the function value. You know, I just plug x into this, and then when you see x approaches, you know, here x approaches 1 from the left, you see this on this picture. That means this point approaches to this hole, right? So the function value f of x approaches to what? To this guy. And this is 3. How can we find 3? Yeah, we see 3 right here. 1, 1, 1. So you have 3, right? You just plug 1, 1, 1, you get 1 plus 1 plus 1, which is 3. Okay? So when x approaches 1 from the, this is from the right, right? You can see that the function value approach 3. And when x approach 1 from the left, so this is from the left right here, and you have this point approach to this guy, to this hole, right, from the left. And you also see that, yeah, actually, you know, the function value approach 3 too. Is that correct? So what is 3 for the function f of x when x equal to 1? What is 3? That is the limit of this function when x approach 1. So alright, this is the limit of x cubed minus 1. X minus 1 when x approach to 1, right? Equal to 3. You see that? So basically, you know, yes, the limit is what? When you consider some special point right here, in this case x equal to 1, right? You let x approach to 1 from the left, or you let x approach 1 from the right. You consider the function limits, the function values. You consider the function value, you know, right here, approach to 1 value 3, and from the left, this also approaches 3 from the left. So in that case, you know, the number 3 is the limit of the function at x equal to 1. And if we pay attention, that is what? That is 1 squared plus 1 plus 1, which is 3. So you can calculate 3 using another function. Okay? So, you know, this is a very, very typical examples about limits. Makes sense? You know, when the function is not defined at some point, but the function has the limit at that point. Let me write that in here. Y, the function f of x equal to x cubed minus 1, x minus 1 is not defined at x equal to 1, but the function has limit at x equal to 1. Okay, of course, you know, some functions may not define at some point and does not have limit, right? Okay, but you know, some function is not defined at that point but has limit. So, you know, if we summarize this, right? So you can say, yeah, you pick a sequence of points from the left of 1, you pick a sequence of points from the right of 1, and then you calculate the function values, right? And then you see what, you know, how two sequence converge, right? If they converge to the same point, so you have limit, is it? Okay, let's consider another example. Now we have function f of x equal to absolute of x divided by x, and we need to find the limit of this function. Now I hope you are okay with this, right? Limit of the function when x approaches 0. Okay, so as we have seen in the previous example, we need to choose a sequence of x approach to the point from the left and from the right. You see that? Right? You know, and we need to do that in this example, right? So let's consider two cases. This case 1 x approach 0 from the left. So what does mean x approaches 0 from the left? That means, x is on the left of 0 all the time, right? That means x less than 0. Makes sense? So when x less than 0, absolute of x is equal to negative x because of this condition, x less than 0. Okay, let me remind you about the definition of absolute of x, right? So absolute of x is equal to x when x greater than or equal to 0 and equal to negative x when x less than 0. And then forget, what is the absolute, right? That is the distance from x to the origin. So if x is bigger than 0, means x in here, the absolute is just equal to the x, right? Because that is the distance. But when x is in this side, right, means x less than 0. So the distance should not be x. That should be negative x, right? That's why we have this, okay? So when you see absolute functions, yes, we need to consider two cases, right? When the inside is bigger than 0 and the inside less than 0. All right, when x approaches 0 from the left, x less than 0, absolute is equal to negative x. In that case, we have the function f of x is equal to negative x over x, which is negative 1. You see, because absolute is already equal to negative x, right? And then, of course, we have limit of f of x in this case when x approaches 0 from the left. Let me write like this. From 0 from the left. That means from 0 with the negative, okay? Equal to the limit of a constant negative 1 when x approaches 0 from the left. Of course, that is negative 1, right? You don't change anything, right? This is negative 1. So if the function is negative 1 all the time, this is 0. So you just, you just have that. Make sense? Just negative 1. Okay? So the second case, when x approaches 0 from the right, that means x is on the right of 0, right? So x is bigger than 0, bigger or equal to 0, okay? Bigger than 0. Then we have absolute x is equal to x, right? And then the function f of x is equal to x. Okay, let me copy this again, right? It's just x over x, which is 1. Again, the function is constant. So the limit of this function when x approaches 0 from the right, I write from 0 with plus, okay? If we approach 0 from the left, I write 0 minus. If we approach 0 from the right, we have 0 plus, okay? This is equal to the limit of 1 when x approaches 0 from the right. Of course, that is 1, right? So if I draw that picture on the same system of coordinate right here, I have the following one. This is 1, this approach from the right. So what can we see in this picture? The left limit and the right limit, right? This is called the left limit. The left limit. This is the right limit. They are different. So that means, the function should not have limit when x equal to 0. Because, you apply to 0 from the left, you have negative 1, and, approach 0 from the right, you have 1. They don't match, right? If you approach from the left and you approach from the right, you get the same value in here. Yes, we have limit, but in this case, no limit. And you can see that. I write right here, the limit of f of x when x approaches 0 from the left is different to the limit of the function when x approaches 0 from the right. From here, the function does not have limit. At x equal to 0. Done. In order to finish this section, I would like to consider 2 more examples. Okay, and those examples in here are very typical, so I hope that you understand them because we will use them in the future. Now I need to find the limit of function 1 over x when x approaches 0. Okay, and I write another limit right here so we can compare them. The limit of 1 over x squared when x approaches 0. All right, so like previous example, we need to consider 2 limits, right? Left limit and the right limit. Okay, don't forget that. The left limit and the right limit. Because we already know, right? If the left limit and the right limit are equal, so the function has limit. Otherwise, the function does not have limit. Okay. All right. So what is the left limit of the first one? Let's say I call this the first. I say this is 7. The left limit means x less than 0, right? I write here x less than 0. So when x less than 0, 1 over x is negative. Okay. We have 1 over x is negative. And you can see, you know, when you divide 1 by a very small with a negative, right? So 1 over x will go to negative infinity. How can we see that? Like you can pick like x equal to negative 1, negative 0.1, negative 0.01, and so on, right? And you consider 1 over x right here, which is equal to negative 1. And in here I have negative 10. In here I have negative 100, and so on. So that means, you know, when x approaches 0, right, very close to 0, but from the left, you know, the function value 1 over x just approach to where? To negative infinity, right? Okay, so the left limit seems like equal to negative infinity. I just do some summary here, equal to negative infinity. Of course, right now we don't know about that, right? But we can imagine about, you know, the picture. All right, so what is the right limit? That means when x is bigger than 0. Again, I have 1 over x is bigger than 0, right? It's bigger than 0. And when you divide 1 by very small but positive, you can imagine 1 over x goes to positive infinity. Why? I can choose the following. Just an example. So I can pick x equal to 1, and then 0.1 closer is 0.1. So you want closer, you can choose 0, 0, 1, and so on, right? You know, they approach 0 from the right. So what is 1 over x in here? That is 1. In here I have 10. In here I have 100. In here I have 1000, and so on, right? Just, you know, the number, the function values increase to infinity. Okay? So I can say, yeah, the right limit in this case is equal to positive infinity. And of course, they are different. You see this? They're different. So, in summarize, I say, yeah, the function 1 over x does not have limit at 0. Because the left limit and the right limit are different. Don't forget this, right? We use this in the future, right? The function 1 over x does not have limit at 0, but the function 1 over x has The left limit and the right limit, simply they are different. That's it. Okay? All right, so let's move to the next one. 1 over x squared, okay? Let's consider the left limit. No problem. When x less than 0, we have x squared right here, right? We have x squared. So whatever, x less than 0 or bigger than 0, x squared is always bigger than 0. Okay? I always have x squared bigger than 0. That's it. And then when x is very small, right, or when x is very close to 0, 1 over x squared is close to 0. Oh no, close to positive infinity. How can we see that? So you can see the following one. Yeah, I can pick x equal to 1, right? And then 0.1, okay, 0.01, 0.001, and so on. So what is 1 over x squared? Is 1. So you have 10 square, you have 100 square, you have 1000 square, right? You see, the number just increased to infinity, right? That is about when x bigger than 0. But when x less than 0, I can do the same, right? X equal to negative 1. And then negative 0.1, negative 0.1, negative 0.001. But you square that, right? 1 over x squared, again, that is just 1. That is 10 square. That is 100 square. That is 1000 square. Again, this increased to infinity. You see that? So, we have x squared in here. That's why, 1 over x squared is always positive. So, when x close to 0, the left limit and the right limit seems to be equal, right? And equal to infinity. So that means the limit of 1 over x squared when x approaches 0 equal to infinity, means positive infinity. Sometimes I don't write positive because, yeah, it's just infinity or negative infinity. So the first limit does not exist. But when you add square in here, the second limit exists and equal to infinity. Look at this. What is the difference? Because here you have power 1. Here you have power 2. That's it. If you have power 3 in here, of course, does not exist. And if you have any odd, power in here, the limit does not exist. And if you have any even power in here, the limit exists. Okay? So, in order to finish this, I would like to draw the graph of these two functions. And then, I think we are good for today. So, the first one, that is 1 over x, is y, x is 0. So you have 0 right here, the breaking point. I have x equal to 1. Here is negative 1, right? I have, for example, 2 right here, so I have 1/2. I have 1 and negative 1 right here. You just plug 1 and 2 into the function. So if we have 1/2 right here, so the function is 2. So I have the following one. For the part x greater than 0, for the part x less than 0, so basically we have a symmetric one. So I have this and this, that's what we have. Okay, the graph of this. And you can see when x approaches 0 from the left, this approaches negative infinity, right? But when x approaches 0 from the right, this approaches positive infinity. Makes sense? That is the graph of 1 over x. And of course, the limit does not exist. The second one is about 1 over x squared. So I have this, x and y, 1 over x squared. When x equal to 1, that is 1. I guess x equal to negative 1, that is again 1, right? X equal to 2, that is 1/4. So I have 1/4 in here, negative 1/4 in here, again 1/4, right? Negative 2. Here's 2, here's 1, here's negative 1, 0 right here. And then when x equal to 1/2 and negative 1/2, we have 1/4, we have 4. 1, 2, 3, 4 right here. Okay, so basically we have the following picture. Port, approach, path to infinity. You see this? So that is the difference between these two examples. 1 over x and 1 over x squared. And in the next sections, we will discuss in more detail about how to find a limit, right, using different methods. So see you in the next video. If you have any questions, please feel free to let me know. Thank you.